Okay, we have an interesting integral today. We've got the integral from 0 to infinity of x squared times e to the minus 4x squared dx. Okay, this is going to be kind of another alternative method. I think the way I did it previously on this one, I did Feynman's trick on this one a week or so back. And I also noticed you could just do, I think you could just do integration by parts. You might need a U-substitution first, but you could basically just do standard methods on this as well. So what I want to do to start is let's just clean up this exponent here. It's kind of tricky having x squared there unless we're going to use the Gaussian integral. So let's do a u substitution. I'm going to make my u equal to that whole thing, 4x squared. Then we'll take a derivative. Du is just going to be 8x dx. And then I think before we substitute, I'm actually going to break up this x squared. To make this work, I can create the 8x. So we'll kind of group like 8x dx to create our du. So I'm not changing it. We'll have this other part that's going to be 1/8 x, just because when you multiply this together, you get back to the x squared. So let's write it this way, but what I'll do is I'll take this 1/8 and bring it out front. We're going from 0 to infinity, x times this stuff, e minus 4x squared, and then we have our 8x dx here on the end. So we have our du. One more thing though, I don't really have a value for x, so let's kind of come over here and solve for x on this in order to set this up. So let's see, if I divide on both sides by 4, we have u to the 4th equals x squared. But then take a square root on both sides, and we have x is going to be square root of u over 2. So now we'll go ahead and substitute it. First, updating our bounds, plug infinity in here. Upper bound still goes to infinity. Plug a 0 in here, we're still going to 0. X is going to be this stuff, so we'll have square root of u. Let's write it as u to the 1/2. And then we're going to have this 2. Let me take the 2 out front, and we'll write it as a 1/2 right here. Then this part's just going to become e to the minus u, and then everything else is just du. Let's clean this up right here. Half times 1/8 is going to be 1 over 16. And then what we're left with here, this is exactly in the right form, or almost exactly in the right form for a Laplace transform. All I need to do is parameterize it. I can create a parameter s right here. And to do this without changing it, we'll just say s is going to be equal to 1. If you're not familiar with Laplace transforms or you need some review, I'll provide a link to the playlist in the description where we derive these formulas. But in this video, all we're going to do really is just use a formula on this. This right here is going to be the same thing as the Laplace transform of u to the 1/2. We have this part, we always have this part as our definition of the Laplace transform, but this is like our f of x or our f of u value right here. So for this right here, let's look at the formula for this. We'll use a different variable for the formula. Let's say if we have something in the form t to the n, we do it a little different if n's an integer, but we don't have an integer in the exponent here. So let's use this formula, where we'll say this is the same thing as gamma of n plus 1 over s to the n plus 1. And actually, let's look at that formula if it was an integer, just because it's pretty quick. Just because by doing this, we'll see the relation of the gamma function to the factorial. So the formula for this would be n factorial over s to the n plus 1. And that's just because when n is an integer, the gamma of n plus 1 is the same thing as n factorial. So we'll just go ahead and use this formula here, but first we've got the 1 over 16 in front. Then we're going to have gamma of n plus 1. So our n is going to be 1/2 here, so it's going to be gamma of 3/2 over s to the 3/2. Now for gamma 3/2, let's try to get this into a numeric form. One thing we can do, it's good to remember one value. Gamma of 1/2 is going to be the same thing as square root of pi. And then along with this, we can use the formula that says gamma of n plus 1 is the same thing as n times gamma of n. So with what we have right here for gamma of 3/2, we can reduce it by 1, and we end up with 1/2 times gamma of 1/2, which is just going to be square root of pi. So what we have for a value on this is going to be just square root of pi over 2. So we can plug this back in here for gamma 3/2. We have square root pi over 2. We'll multiply times 16, and we'll have this as 32 times s to the 3/2. But remember earlier we said s is going to just be equal to 1, so we can just plug a 1 back in here. For my final solution of this, we just have square root of pi over 32. Okay, there you go, another alternative method on this one using Laplace transforms. Thanks everyone for watching. Have a good day.